Centroids and centers of mass. In this section, we are going to find the area and the centroid of 2D shapes that have a functional relationship between x and y, and we are going to be using single variable calculus. We're going to find the area and the volume and the centroid of composite shapes, both in 2D and 3D, using the tabular method. We're going to be breaking those shapes down into more common shapes like rectangles and circles in order to build up our shape. And we're going to be finding the center of mass of non-homogeneous objects, so those objects made of materials of different densities. And finally, we're going to be simplifying distributed loads into a point load or multiple point loads and placing those point loads in the correct locations or the equivalent locations. So we'll begin with, what is a centroid? The centroid of an object is the location on a homogeneous body where we can place all of its weight in the free body diagram. So as the picture shows here, right on the marker cap would be the centroid, or more correctly, the center of mass of that composite object, where the entirety of its mass can be shown going through the marker cap pointing down, and then the marker cap is supplying a normal force that's keeping it balanced. The centroid is also known as the geometric center, or sometimes the center of pressure. Now, in a homogeneous body, so that's an object that has all one type of material or all material of one density, the centroid and the center of mass are the same thing. They're located at the same point. However, in composite bodies, like the picture on the right, then the center of mass and the centroid are probably located at different locations. And the center of mass or the centroid can be located on the body or actually off of the body itself. It's always going to be on the body if the shape is convex, though. Finding the centroid or the center of mass not only lets us simplify all of the mass in the body to a single point, but it's going to allow us later in this section to simplify distributed loads to an equivalent load acting at a single point. So if we have force on our object due to something like sand or snow where it's distributed across the body, we're going to be able to simplify that load to a point load and then work with it as we have been previously in this semester.